And again, as you're coming in, we're live. We're just waiting for the queue to fill up here. Tried to get Lynette to sing a song while we're doing this, but she's still finishing her presentation. Can you imagine that?
I finished that 5 minutes ago, I'll have you know.
Hello, everyone, and welcome to the 2024 ICPSR Data Fair, Anchored in Data Reality. We're happy to have you join us today for this webinar titled Invalid with Any Code. I'd like to give a warm welcome to our wonderful presenter, Lynette Holter. She is the Director of Instructional Resources here at ICPSR, although she wears about 3 dozen other hats. So we welcome her and we thank her for what is always an interesting presentation. And Lynette, the floor is yours.
Thank you, Linda. And welcome to everyone. Linda, you did not need to mention earlier that this was one of the most popular webinars in terms of pre-registration, because now I'm nervous. But anyway, hopefully you'll learn something throughout this afternoon, and if not, you'll have an hour to get a good nap in. What I thought we would talk about today is that there really are kind of 2 approaches to data, and invalid with any code means different things depending on which data approach you're thinking about or you're taking. Then I thought I'd talk about the main things to think about when you're approaching either data or analyses, and how ICPSR metadata can help with these things. This is not a new issue. There. And so some of you have probably heard me present on something like this before. It's just becoming more and more relevant, I think. I wasn't sure that that was possible even 5 years ago, but I think it is. And hopefully you'll see why in just a minute. I wanted to outline, before we begin, that there's sort of 2 separate approaches to data as I kind of think about it. And these are really more of a continuum. They're not like opposite of each other, but I think it's important to be aware. The first is the one we're probably most familiar with, which is sort of the hypothesis testing or theory-driven approach, where you find some data, you have a research question, you find some data that you think will help you answer that question, you run your analyses, often with the goal of understanding some social problem or social phenomenon. We do often use that. We try to predict outcomes. And usually in this sort of data work, science builds on itself. So the place that those research questions come from are often an understanding of what other people have done before it. The other sort of approach in using data is machine learning or data science. These things have very specific meanings. I'll probably use them interchangeably. That's probably not the best thing to do, but they're close enough that I'm kind of okay with that. What I'm using them to mean is an approach that allows the data to speak for themselves. So you don't necessarily go in and look for something. The patterns just emerge. And the key with this is that it takes lots and lots of data. And because it takes lots and lots of data, it's also often resource intensive in terms of the electricity it takes and the space it takes to save and manipulate those data, things like that. So when you're thinking about big data, this is kind of that model. Within machine learning or a data science perspective, you can have what are called supervised models and unsupervised models. Basically, it just means kind of how many parameters you're going to specify at the outset. If you want your models to pay attention to a particular characteristic or factor or something like that, then you might want to put in some of those parameters and you'd have a supervised model. It might be that predicting outcomes is a goal for this kind of work as well. But the key difference is that you're not going to understand everything that's going on under the hood. So if you run some code and you get a result that tells you that your model fits the data really, really well, it might tell you that you have 700 different factors represented in your model. It's very difficult to get a sense of what each one of those 700 things might be. And so that kind of understanding that we look for when we're looking in sort of more of a hypothesis testing realm is harder to get at when you're letting the machine find the patterns. And so I just kind of wanted to point that out. I'll try to point out as we go which ones of the things to think about are more or less relevant for each kind of data work. So why did we decide to have this session in the first place? Aside from the fact that Linda came up with the great title and we decided that we just needed to use it. It's actually getting really easy to analyze data. And I put easier in quotes in the heading of this slide because those of us who know data know that it's not actually easy. But it is easier to get data. So with web scraping and I note here that it's easier and easier to collect data through surveys. There's lots of different programs that will now collect data. You may have noticed the number of poorly written surveys that you might see. So it's easier and easier for people without training or background in research to contribute to the data that are out there. It's also, I remember hearing these arguments when I think SPSS may have been the first stats package to go to sort of a menu-driven approach, and people took a moment and sort of stepped back and said, wait, this is going to allow people to do things that they don't understand. It turns out that that's right, and that today that message is writ even larger. So not only do you have the menu-driven stats packages that make it easier to find specific commands, but you also have artificial intelligence that's generating or being made use of in code libraries, such as CodePilot in RStudio or Google's Gemini if you use Jupyter Notebooks in Google Lab, Google's Colab space. You'll notice that when you put in a text box where it asks for you to put in your code, it gives you the option of writing the code yourself or asking AI, in this case, Gemini, to generate that code for you. So it's even easier to do things that you have no idea what they actually do. And even just searching in Google, this nice image that I have here is from a LibGuide, I think from Reed College. I have it hyperlinked so you can find it. But I just asked it, okay, how do you do a regression in Stata? And it gives me not only the commands, but the different options that I might use, and then an example of the code that, or the results that are generated. So it's super easy to run something against some data. But as these images hopefully show, just because you can do something doesn't mean that you should do something. So not all data are created equal. Not all data or not all code should be run against all data. There are lots and lots of characteristics of data that you really need to understand before you can think about what's appropriate and what commands or syntax you should actually use, what strategies you should employ to analyze those data. And again, if you're interested in any of these images, I have them hyperlinked as well. So what is it that you need to think about? And many of you are probably aware of these. You'll probably be aware of some that I forget. So if that's the case, feel free to pop it into the chat or the question and answers. or the Q&A box, and excuse me, and let me know. But these are the things that I think about when I'm approaching data. And I noted on that previous slide that it's really, these are the things that you need to keep in mind when you're looking at both data that you might use, or if you're working with a student or a faculty member that they might use in answering a particular research question, but it's also what you might, the kinds of things that you want to think about when you see results presented. The same kinds of questions come into play. So the first thing, of course, is where do the data come from? Is it from a trusted source? Is it from, is it a federally funded survey that's run by someplace like the University of Michigan's survey research operations, who know how to do surveys and who know how to write good questions and things like that? Are the data likely to be credible? Is the organization that made the data available, do they tend to have a bias in one direction or another? Can you tell that? Is the source unknown? If the source of the data is unknown, that's a big red flag. And also, now more and more data come from what we call like naturally occurring sources. So maybe it's transaction data, or data from your Fitbit or other kind of whatever those watches are called, the watches that are supposed to get you moving, Fitbit, things like that. All of that can become data. But the thing is that we need to remember where it came from and what the implications are, depending on where those data have come from. And we'll talk a little bit more about that as we go on. But I'm going to jump to the next thing to keep in mind, which is closely related to where did the data come from, but it's who is included in the data, or what's included. If you're using transactional data, what kinds of transactions are included? And just as importantly as in thinking about who's included is who's left out. I don't know about you, but my cell phone is constantly pinging me these days with requests to respond to surveys about who I'm going to vote for. And so far, I have held off and not answered a single one of those, which I probably should not admit in a presentation about data use and surveys. But it's true, in part because I don't know where they're all coming from and things like that. But think about who is left out of the data, both by opting out and by design. You also want to think about with samples, how many people were included. And this is both from you don't want a super small sample. So if you've got a study that has a sample of 10 people, chances are, even if they're randomly drawn from some pot, they may not be representative of the larger population. Even worse is a sample of 10 people who are just happen to be in the office on a Tuesday or something like that, because they're going to be different than the people who aren't in the office on a Tuesday. And relatedly, thinking about how people were included or excluded. Was there some criteria that they needed to meet to be a part of the study? And I have people in these last two questions, but it really can be anything, whatever your unit of analysis is. If you're using machine learning, it might be images, or it might be batches of text, things like that. So knowing who, how many, and how items were chosen for inclusion in the data set is critically important. People often think just because a data set is large that it's representative. It's more likely to be representative if it's large, but really, and this is sort of me going back to my research methods purist inner core, you have to have some level of random assignment or random inclusion, randomness in the choice to be included in the sample. to really be able to say that your sample is representative of any group. I like to, when I'm teaching, I like to tell students that I could probably give them a really good sample of about 110 people on a Saturday, 110,000 people on a Saturday afternoon in the fall. But it may not be representative because I would be like just going to the, the U of M's big house stadium and giving people there a survey. The people who are inside the big house on a Saturday afternoon are very different than the people who are not, or people like me who try to stay as far away from there as possible. Not that I don't like Michigan football, I just don't like that many people. Anyway, so moral of that tale is big doesn't always mean good enough. Sometimes it does, but not always. Another thing to keep in mind is how the key constructs or what it is that you're interested in. How are those being measured? Obviously, you want to make sure that they are there. If you're looking for data to analyze to answer a particular research question, you want to make sure that your key concepts really have been measured. And then you want to take a look at what exactly was asked, or what observation was made, or what data point was collected exactly. Because things like question wording matters. How you ask whether someone's going to vote for Harris or Trump may lead to very different results. And then the other thing to keep in mind is what I call definitional issues. And I think I got this, I didn't make up this term. I think I got it probably from Joel Best. But has anything changed in the way we define the particular thing that you might be looking at? A common example that people use to illustrate this is that the United States changed how we conceptualize obesity. And all of a sudden, we went from having, some percent of people who fit that category to having a much larger percent of the population who was classified as obese. The individual people didn't change anything, but the definition of how we classify someone as being obese did change. And so all of a sudden, a lot more people were included in that definition. So that's the kind of thing to think about, particularly if you're using older data or data from a different culture, for example. Think about those definitional issues behind this that are going on behind the scenes. So in terms of thinking about variables, I just wanted to take a second and see what you think this chart might mean. So this is a cross tabulation of mother's education and blues. That's the variable name. And so just take a minute and if you want to put your thoughts in the chat or put them in the Q&A box, maybe Linda will read them to me as they come in. But think about, what is this chart telling us? And if you need a hint, the reason that I picked these two variables is because one of them has, oh, good one. Turns out I can see the chat. And someone just posted how many moms get depressed after giving birth, and how that's correlated with their education level. Good one. Looks like the general population. It is the general population. I'm looking for, what do the two variables mean? Oh, good ones. Looks like it's saying that the moms who have more education are not as likely to get depressed. That does look like exactly what it's saying. Oh, and somebody else asked about the sample sizes. Yep. I purposely left those off. This actually is looking at mother's education and, oh, good. Yeah, somebody asked, but what does blues mean? Postpartum or anytime. And actually, what it means is whether you listen to rhythm and blues music. So if you had seen something like this in some public report, you would know that it's a definitional issue. You don't know what blues means. So in this case, it looks like women whose mothers have, or individuals whose mothers have more education are more likely to listen to the blues than individuals whose mothers have less education. But overall, the trend is that most people in any category don't listen to the blues. And whoever asked about sample size is exactly right. If you were to encounter something like this in the real world, you'd want to know how many people were in that sample. In this case, it's from the Survey of Public Participation in the Arts, but I didn't use the weights. So that's another step that you need to think about. So this is just the raw percentages. So it represents only those people who were in that particular survey. It's not representative of the US. So I just wanted to give you a sense of how important it is to know what a variable is actually measuring. This is one of my other favorites. And probably many of you know this website, but just because two things are related doesn't mean that one causes the other. And I've been using this spurious correlations website forever now. But I just noticed that they have actually invoked AI not only to come up with the patterns, because if you read the documentation of the website, he actually generates these correlations through machine learning. So it's just tons and tons of data and trying to look for the patterns. But they now invoke AI and try to give you an example explanation for why these two things should be correlated. I don't know if you can see the titles super clearly, but the first one is the popularity of the first name Annabelle is highly correlated to UFO sightings reported in Maryland. And the second one is the number of mobile heavy equipment operators in Maine is highly correlated with customer satisfaction with Verizon. These things have no underlying rationale to be correlated. And yet the computer found these relationships. So just because two things are move in a pattern does not mean that one causes the other. And you want to think about when you come across something like this. As a real world example, I just heard about a study that says that people who have more flexibility are likely to live longer. And so they were encouraging people to think about their own flexibility, like physical flexibility, and what that means for their life expectancy. Now, what they didn't talk about, and I haven't had a chance to actually look this up, I just heard it on the radio yesterday, was whether they're controlling for anything like physical fitness or anything like that. There are a lot of things that could cause both a particular life expectancy and the amount of flexibility. So it's not necessarily just because two things are related that one causes the other. It could also be that I just lost my train of thought. I had another explanation for that relationship and I just lost it. But we will just move on. The other thing to think about is significant in what sense? So a lot of times you'll hear, or if you're looking at published articles, things like that, you'll see that two things are significantly related, or one group is significantly better or significantly worse on your outcome measure than the other. Just because things are statistically significant, or there's a statistically significant difference between two groups or three groups, doesn't mean that they're actually important. And I love this this website. Again, it's hyperlinked. The image is hyperlinked as well. But things like the size of your data set. If you've got a large data set, you've got huge statistical power, which means that you're going to find just about anything that you try is going to be statistically significant. When you're working with a data science model, one of the things that they always try to see is how well does your model fit the data. So they train the model on, sorry, my whiny cat just came up next to me. They train the model on a set of data. They often hold a piece of that data behind and then try to test it on that and see how well it does. It may do really, really well on your training data, but it may be that you're finding patterns that are just noise. It's finding the correlations among the things that are noise. And so when you try it on the new data, it doesn't work nearly as well. Data scientists would call that overfitting your model. You're trying to take too many things into account, and because you've got enough data, they're going to look like they're statistically significant, but it's really hard to tell what's going on. If you're doing hypothesis testing, you might think about this as using the sniff test or the smell test. Does something smell fishy in, okay, that was my cat. She doesn't trust these things either. If something seems too good to be true, it might just be, is basically the point there. So think about, does it actually make sense? Does this statistical significance, is it practical significance? Lots and lots of tutoring organizations have programs for the different standardized tests, the SAT, the ACT, things like that. And they show that their results are that students who pay a lot of money and take their classes do significantly better than people who don't. But often when you look at the underlying data, it's 1 or 2 points better. It's not really an important difference. So that's the kind of thing to keep in mind. Kind of following along this vein is margins of error. And you really want to see whether these are presented at all. Sometimes people don't present them, and that tells you something right there as well. But also thinking about what the results mean in the context of that particular margin of error. So the graph that I have here is shows that Harris is leading Trump 48% to 45.4%, but the margin of error is plus or minus 2.7 points, so, or percentage points. So if you put that margin of error around those two numbers, you'll see that it really overlaps. So we can't tell. This is from 538, and it's from earlier this week, or end of last week. So we can't really tell who's going to win the election. It's really, really close. These things are often not taken into account when presenting results. So there are a couple things to keep in mind with presentation of results. Namely, are the charts and the graphs actually reasonable? Do they make sense? Does the y-axis start at 0? This is probably the thing that gets violated the most often. So if you look at the image in the upper right, you've got a headline that says President Trump crushes Biden in Pennsylvania. Obviously, this was earlier in the race. But it's 47% to 46%. Those bars look a lot more different than just 1%. And then also looking at If you've got any kind of categories, are they in order, or has somebody moved some of the categories so that it looks like there's a trend when there actually isn't a trend? Do the results tell the same story as the headlines? The smaller graphic, the title says the number of artists generating at least 1,000,000, 100,000, and 10,000 has nearly tripled since 2017. But if you look at the numbers, like you've got 11,600 that's way taller than 23,400. Basically, this just, if I were to look at this, even the size of the bars aside, it basically just tells me that there's probably about the number of artists has probably tripled, something like that. It doesn't really look newsworthy. Thinking about particular limitations that the data might have is also important. And sometimes people are kind enough to point these out. If you're looking for data to use to answer a particular research question, how might other people who have talked about the data and their limitations, what does that tell you about how useful the data will be for your own research question? For example, are you trying to establish causality in two things? Are you trying to show that a program, for example, affected an outcome on health or on behavior? If you are, you need data that are collected at 2 points in time. You can't have a single point in time and say, yes, this thing causes that thing. You don't know that. They happen at the same time. They're being measured at the same time. You have to think about whether the question is worded the way that your research needs it to be. And probably one of the best examples of this that I always come back to is my doctoral dissertation was on perceptions of fairness in household division of labor. But the question that measured perceptions of fairness was actually really, really weak. It basically asked individuals if they thought that that the housework was that the division of housework was fair to them, and it was a yes no. So not the best. It was the best way to get the degree done at the time, but not the best measure of perceptions of fairness. So how does the question wording relate to your own research question? Is it a convenient sample? If it is that what you really want? Do those people represent anything larger than the people who happen to have been at that place at that particular time? So thinking about those kind of limitations to the data. If it's data that you've scraped off the web, again, what's left in, what's left out, that kind of thing. Even if somebody doesn't lay out what the limitations are, you should think about it to think about how it affects your take on the whether the data are suited for your question or the analyses that are being presented. And metadata can actually help understand what's going on in the data. And this is where ICPSR is particularly strong. I bet you didn't think that, you know, an ICPSR data fair presentation would be a infomercial for ICPSR, but you know, it happens. So metadata really is one of ICPSR's strengths. If you look at other places where people are sharing data, there's often very minimal information about the data themselves. So you can't ask the kinds of questions that I've just talked about. We have a professional curation staff. Often the project management staff also help creating a metadata record or a record that describes each study. And to do so, they're looking at all kinds of documentation that's provided by the data producer. So they might give us a questionnaire, they might give us information about their methodology, they might give us an interviewer guide, they might give us initial reports that they've put out. The curators look at all of that when they're putting together that description of the data. They might also look at things like publications that have since used the data and how do they describe the data, or looking directly back at some of the project websites. They'll get information from there. So they're trying to find all of this information and pull it together so that somebody who wasn't a part of the original research team can understand the strengths and limitations of the particular data. And you'll see in a minute that this includes information about the sample, the methodology, all of the pieces that are important to think about when you're trying to evaluate whether the data are useful. So we have recently launched new study homepages. The first one is an example of our sort of long-standing study homepages you might be most familiar with. One of the smaller data collections, NANDA, has recently gotten sort of a facelift in terms of study homepages. So they look a little bit different, look a little bit more updated, little bit different navigation. It's down the side instead of across the top, but the same information is contained in either place. So you can see you'll always get a description of or a summary of the project itself. You'll get information about when the data were collected, from whom they were collected, any other methodological information that's key. You'll get information about whether this was collected through a web survey or a face-to-face interview. All of those kinds of things. People who are methods geeks know that that actually influences how people answer sometimes. You'll also get information about who funded the data collection. So this helps you get back to that source of the data. It gives you information about who the principal investigators were, who the participants were, who the funders were, so you can make your judgment about credibility that way. It also tells you, are there common scales included in the data? So for example, if you're studying depression and you want to use the Beck Depression Inventory or something like that, it'll tell you if that's included in the particular data set that you're looking for. And then you'll know that the questions are asked in the way that you need them to be. I wanted to highlight that there's also, for those of you who haven't looked at our website in a little bit, not only is there that study level metadata that gives you an overall sense of what's in the data, but the variables level metadata takes you that one step deeper. So this tells you what variables are in the data. And if you click on any of the variable names, you actually get a frequency distribution and you get to see where that was in the, where it sort of falls in the data set. So you can see what's before it and what's after it, because often that context is important as well. We saw that when they were changing the way race and ethnicity was asked in lots of federal surveys. People answered differently depending on what's asked first. And then also I would point out that the example that I used for this is one of our most recently released studies. So it only has one citation, or one related publication. But many of our studies have long lists of publications that have been related by our librarians. That helps tell you a couple different things. So it tells you what kinds of topics have been studied using these data. Many of those articles end with a section that talks about the limitation of that particular research. So that helps you answer those questions about limitations. It can also tell you, were these data used in conjunction with any other data that ICPSR holds? That's listed right in the bibliography entry as well. So to recap, always think about, how do the data fit the research question? Whether it's your own work or you're helping someone else find data to answer their research question, or you're looking at something that's been presented in the media. are the data right for the results that are presented or the research question that was being asked? And just a reminder to be wary of extra small samples. If you've got 10 people and 3 of them do something, does that mean that 30% of the actual population is going to do that thing? Maybe, maybe not. But also be wary of really, really big samples, just knowing that you're likely to find statistical significance much more easily in those large samples. So make sure that you've got a theoretical reason for thinking that your results say what you think they say. Again, if you're doing the sort of the traditional hypothesis testing. Be wary of question wording. Be wary of things like opt-in surveys or opt-in data collection efforts. Again, that's probably not going to be the most representative. People who decide to do something are often very different from people who decide not to do it. Statistical significance isn't always meaningful. Causality isn't always what it looks like. And then lastly, one of the things that I wanted to mention is be aware of fraudulent data. I have spent way too much time over the past couple months going down rabbit holes on Retraction Watch. If any of you are familiar with that website, they do a great job of finding articles that look like their findings are kind of hard to believe, and researchers will challenge the findings, and there are a number that have been shown to be completely made up. I was looking at one just the other day that was particularly startling because it was someone who studies honesty, among other things. And they could show, her data were in Excel, and they could show how she had manipulated the different cases. In that particular instance, she had moved cases from one condition to another so that it fit the results that she was wanting. So even though that's not super common, it is probably more common than we would like to think. They also note on Retraction Watch that one of the biggest, most heavily cited studies of Alzheimer's disease was actually proven to be false. They had done some data manipulation there as well. So that's getting easier and easier too. So don't discount that if your brain is going, wait, that doesn't make sense. There was a great line in one of the evaluations of an article for Retraction that said something like, basic laws of mathematics and physics would have had to have been broken for these results to be possible. So sometimes it happens. And I think that is all I have for now. So if you have any questions, I'd be happy to take those. If I put you to sleep, I'll try not to wake up your nap. This is just a reminder of how you can connect with ICPSR. And I think I am going to stop sharing my slides so that I can see you all. I guess I can't see you all, but at least I don't have to just look at my slides. Oh. Okay. Any questions? I've done it again. Everybody's asleep. Gotta love it.
It was just a thorough presentation.
I do see a question from Paula Lackey, who knows more than I do and should have done this presentation. But she asked about sharing a link for the false findings site. I think the one that you're referring to, Paula, is the thing that I mentioned last, which is Retraction Watch. The other things that I used in the slides are linked either to the image or on the slide where I talked about them. She also asks, have we found any changes in undergraduate research behavior as it's gotten easier and easier to make a mess of things? Sadly, yes. Especially now with things like Jupyter Notebook, where it's easy to just or GitHub repositories for code, where it's easy to just take someone else's code and dump it in and run it against your own data. There seems to be a much more, maybe it's just that I'm hearing about it more, but it seems to be more prevalent that people are doing things like that without thinking about what does this code actually do? Or they're running something because their friend ran it without really thinking about, does it make sense for my data? Or they found a great type of graphic and they want to replicate that using data that aren't measured at the right level of measurement to make that kind of graphic appropriate. And then it's interesting when you read some of their some of the impressions of the findings. That's when you really start to realize they don't entirely understand what it is they're doing. On the flip side, I will also say I served on a panel to look at papers that were written by groups of students in intro stats classes, and they have done some really cool things because of things like machine learning. There was a group that looked at a particular artist's songs and looked at like the tone of the songs and the different themes and the actual audio quality of the songs. Because this kind of information is out there, and so they can make use of this new kind of data and the power of Python and R to help analyze these kind of things. So it's kind of going both ways. There's some really impressive stuff and some really kind of scary stuff. I guess that's no different than research in general. Another question. What is the most important thing we can all do to contribute to educating the public, and sadly many of our colleagues, about these important considerations? Those of you who have heard me speak before, you could probably guess what my answer is going to be. But I think one of the things is addressing this kind of thing in class early and often. I'm a big advocate of using data, even right from an introductory level course, and trying to get students to start thinking about this. It really is a mindset and it takes practice. So I think the more exposure we can have to these kind of things, I think that's good. I don't know what to do in terms of general public, where it seems like people are willing to believe just about anything. I don't have a magic silver bullet for that. But I think, I don't know, my goal is to just kind of keep trying to model this, you know, asking the right questions and things like that. That's the best I can do.
Thank you, Lynette, for an always interesting presentation on why metadata and good data and understanding it all is really critical for science and for just every day. So I'd like you to invite you to come on back tomorrow promptly at 11 a.m. We will be talking about the ICPSR summer program, and that's in quantitative methods of research. There will be all kinds of new tidbits that the program's been changing and evolving as technology has changed and evolved. So lots of cool new things. If you haven't talked or visited the summer program in terms of how it runs and what it is and what it contains, in a year or two, you should definitely attend. They'll also talk about a lot of the scholarships that we have available. If someone at your institution hasn't gone to the summer program in a while, you really should take some time to hear about next year's program. So,
And you just reminded me, Linda, I put in the slides and forgot to mention it at the very beginning. I said that that understanding the statistics behind the research is important, and I linked to the summer program because that's one place where you can get that understanding. And I forgot.
Awesome. Yes, absolutely, absolutely. So it all runs together, doesn't it? So all right. With that, thank you so much, Lynette. Thank you all for attending. And we hope to see you throughout the week. And have a wonderful evening or afternoon, depending on where you are joining us from. Take care and thank you.